So for you theory enthusiasts out there, I'm going to briefly overview some theory about coordinate transformations. And then I'm going to highlight this with some examples from cylindrical coordinates and spherical coordinates as well. So starting off, we're going to look at this with just a generic coordinate transformation. So let's say that I start in the UV plane, and I have some region in the UV plane. And then I have some coordinate transformation t that transfers my coordinates into the xy plane. Now, under this transformation, my original region isn't going to look the same. It's going to get all squishy or tilty, depending upon whatever the transformation is that we were looking at. Now, recall before, when we were splitting up our original region, we would break our region up into little rectangles. And if I highlight one of these rectangles, let's say that we're talking about the rectangle that's at the point, has base point at u naught, v naught. And we know that the side lengths were given by delta v and delta u. And this area here, I'm going to call delta a star. But under the transformation, this coordinate system is going to shift, right? It's no longer going to be these straight little rectangles. It might be something all crazy and curvy-like. So if I have some crazy and curvy-like sections, now my new section, I'm going to have a new point here. Let's call this new point t of u naught and t of v naught. Those are my x and my y inputs. And in this case, this rectangle is shifted. It no longer looks like a rectangle. It would look like, some other crazy sort of shape. But because of our power of calculus, we can approximate what this shape looks like with a parallelogram. So I'm going to draw in a parallelogram here that is the transformation under this function. Well, what is this parallelogram? The direction vector here, and maybe this is a little more vector theory than we have covered in this class. The direction vector here is going to be given by the partial derivative with respect to u of this transformation function, evaluated at the point u naught, v naught. That's the direction of the vector. But it's going to have magnitude delta u, because that was the original length. Well, what is this? What am I talking about when I say it's the derivative with respect to my t function? If I write this out longhand as a vector, this is a vector, the vector in this case is going to have an x component that's given by the partial derivative of my x coordinate dx du evaluated at u naught, v naught times delta u times the partial derivative dy du. It is, okay. dy du at u naught, v naught times delta u. That's totally not on the camera anymore. I'll rewrite this in bigger font later. Similarly, my direction vector up here is going to be given by the partial derivative tv at the point u naught, v naught, and the length of it is going to be given by delta v. These are our unit tangent vectors, right? And that's why I need to scale them up or down by the width of our dv's. So what does this mean? It means that the new area of this new patch of rectangle is not the same as the old area of the old patch of rectangle. And really, we know how to find the area of patches of rectangles, because in this case, it's a parallelogram. So it means that the area of our delta A, meaning the area of this parallelogram that's in blue, is going to be given by the magnitude of the cross product of these two vectors. Tu at u naught, v naught crossed with tv at u naught, v naught. Because the magnitude of the cross product is going to be exactly equal to the area of that parallelogram. And as I limit out to get smaller and smaller parallelograms, it's going to become a closer approximation of the area of this region under this coordinate transformation. Summarizing what we saw before, we know that one of the sides of the parallelogram is going to be our unit tangent vector, the partial with respect to u, times that magnitude delta u, which is given by this. All I'm doing is I'm taking my x-coordinates of my u vector and taking the partial with respect to u, and the y-coordinates and the partial with respect to u. The same is analogous for my v vectors. So when I want to find the area of the parallelogram, all that I need to do is take the cross product of these two vectors, which in shorthand I got rid of the base point u naught v naught because it's tedious notation. So to take the magnitude of this cross product, I'm going to first find the cross product. So in this case, maybe I should get rid of these because I'm just taking the cross product right now. So in this case, most of these are going to be 0, that I end up with my I component is 0, my j component is 0, and my k component is going to be this chunk times this chunk, which ends up being dx du times delta u times dy dv times delta v, minus this chunk times that chunk becomes dy du times delta u, sorry, this should be a u, times dx dv times delta v. So the magnitude of this really is just the magnitude of all of these chunks, and I can simplify this if I wanted to. And I end up with pulling out some u's and some v's and the other pieces. I see that this really is just a differential of my xy function with respect to my uv times delta u times delta v. That's just the distributive property, right? I'm just pulling out these pieces, and so it's the mixed partial here and the mixed partials here. So why is this interesting? Let's go ahead and do an example where I show what this means in terms of polar coordinates. So let's illustrate this coordinate transformation with a concrete example of cylindrical coordinates. So when we convert cylindrical coordinates, we have a coordinate transformation where my inputs are r, theta, and z, and my outputs, the x-coordinate is given by r cosine theta, the y-coordinate is given by r sine theta, and the z-coordinate is just the z. So in order to do this calculation, remember that we were finding our total derivative zxy with respect to all of the variables r, theta, and z. And I want to know the determinant of this derivative matrix. I realize this is some theory that maybe you haven't seen, but I think that it makes sense. So what is this talking about? Well, it's all of my partial derivatives all in matrix form, meaning that it's the derivative of my x component with respect to r, the derivative of my y component with respect to r, and the derivative of the z component with respect to r. The next column of the matrix is going to be the derivative of the x component with respect to theta, the derivative of the y component with respect to theta, and the derivative of the z component with respect to theta. Finally, my final component is going to be the derivative of the x component with respect to z, the derivative of the y component with respect to z, and then the derivative of the z component with respect to z. And I'm using my function here to compute each of these partials. So in this case, we see my partial derivative of x with respect to r is treating r as my variable and cosine of theta as my coefficient, and I end up with just cosine of theta. Similarly, when I take a derivative of my y component with respect to r, I end up with just the sine of theta. And when I take a derivative of my z component with respect to r, I end up with 0. Shifting to the next variable, theta, the derivative of the x component with respect to theta is going to be the derivative of cosine of theta, which is negative sine of theta, where r is just the coefficient. The derivative of sine of theta is going to be cosine theta, where r is the coefficient, and the derivative of z is 0. Finally, the derivative of the first component with respect to z is 0. the y component with respect to z is 0, and the derivative of z with respect to z is just 1. So when I look at the determinant of this matrix, notice what I get out. The determinant is going to be cosine of theta times r cosine of theta times 1 times minus 0. So I end up with cosine of theta times r cosine theta plus 1 minus the zth component, which is negative r sine theta, all times this minus this times this, which is just sine theta, plus 0 times this minus this times this, which is just 0. So in conclusion, it means that the determinant of this matrix is going to be r cosine squared theta minus a negative r sine squared theta. I can factor out the r, and I get r times r, which is 1. So what did this just tell us? I did all of this work, and I found out that under a cylindrical coordinate transformation, when I take the magnitude of this, recall that this is the area of that parallelogram, I find that it's a function of r. And this is exactly the differential that or the term of integration that we're going to need to add on in order to convert from our x, y, z coordinates into polar coordinates.